Okay, so let's continue to the second part of the trajectory generation, and which is waypoint trajectory, and it is the simplest trajectory because I'm going to introduce a very simple one in order to address the process of finding trajectory and analyze some weakness or challenges for this kind of trajectory, and then we can think further to more to a better trajectory for mobile robot application. So here, let's just consider a point-to-point trajectory generation. So here in the coordinate space, x and y, okay, and let's say I want to move the robot from this point to this point. And at initial time, the robot, orientation is like this. So I mean at initial time, HB is here and YB is also here. Then I want it to move along along the line to the end point here. So here is start point, here is end point. And when it ends here, the robot has orientations like this. Um, yeah. Okay, so it has some angle with respect to x-axis, psi, right? So HB is become like this, YB become here. Okay. So what you know is the coordinate at this point and coordinate at this point of vector H. So capital H at start equal to, well, H, Y, psi at the start. Okay. And then you also know the coordinate here, H at the end equal to H, Y, psi at the end point. Now the goal is to generate H double dot. Oh, yeah, H double dot given this known coordinates and okay, given H S H E maximum velocity. So maximum velocity means H max, okay, because the actuator has saturated input, for example, maximum voltage, and also uh, acceleration. I can say maximum acceleration. Yeah, given okay maximum acceleration. Yeah, h dot max. Okay, and I give you the idea like this, that for the so I separate between H and Y and psi. Let's see psi first, because for this robot, for the mechanism wheel and omni wheel, we can separately generate trajectory for psi and position HY. Okay, we can do it separately. So now I give the idea. Well, um, because first the robot is at rest. Okay, at rest, the angle start psi start, and the angle at the end psi n, psi e, for example. So at a certain time t, it start to accelerate. So he is psi dot, not psi, psi dot. So at the start time, at the start time, it doesn't have to be 0 v. It can be anywhere because from point to another point. So it can be any time, can be anywhere. So at the start time, we accelerate it, and then it reach the maximum psi max, psi dot max. Okay, and before it reach the final, it decelerate. Okay, such that the area here would be psi n minus psi start. You got the idea? Yeah, if the delta psi is too small, maybe you, during the acceleration phase, you don't reach the maximum yet, but you need to decelerate. So there is another case that at the start ts here, you start but not reach the maximum yet, and then you need to decelerate. Okay, so just call it this tn, the also tn. So accelerate, decelerate, and also this area must be, yeah, because phi max is here, upside max is here, sorry, psi dot max. Okay, not reach it, but it come back here. So this area also, okay, but this in this case is small. But how small? What is the condition to separate between this case and this case? Okay, so the first step that I'm going to ask you to write down is, what is the condition that separate between this case and this case? What you know is this delta psi, and you know the maximum psi dot. Okay, and you know the acceleration, maximum acceleration. It means this is acceleration using the acceleration maximum, and this is deceleration maximum also. Okay, you got what I mean? So you have acceleration. We mean the velocity start from 0 and velocity increase little bit. Okay. So if the angle is very far away, I mean you accelerate until it reach velocity maximum, but you still cannot reach the angle yet. So you need to keep that maximum angular velocity until almost it's right there. You decelerate into in order to stop uh, smoothly. To stop smoothly, you need to decelerate, right? You cannot just say, "Oh, but you are right there," immediately stop. Then it means it's like deceleration is infinite. But we don't want that. Okay, so start to think and write down. First, just write down the condition that separate between these two cases. What you know is delta psi, and you know, okay. Now for this one you just take psi dot max, and for this one you just take psi dot, okay, just call it alpha then. Just call alpha. Alpha would be the slope. Okay, just call it alpha. And this phi max, yeah, whatever you can call it, psi dot max, same, or You can name it by other parameter, that's fine. And this one is the slope here is minus alpha. Yes. Because h has h, y, and psi. Yeah, just use the last component because, as I said, you can separate. You can generate trajectory for angle and for the portion separately. So first start to think about for the angle because it's only one component. It's easy. Later we think about how to generate trajectory for x and y with two components. A little bit more difficult, but not so much. Not very difficult. Okay. So what is the condition that separate between these two cases? Okay, I give you the idea. The condition that separate these two cases is the condition that tap that you have the tap size such that you accelerate it to reach the maximum and then you need to decelerate immediately, right? That is the condition to separate. If the tap size greater than that, you may hold the maximum velocity a little bit, okay? But if the tap size less than that, before you reach the maximum, you need to decelerate. Okay. So what is that tap psi? What is the value of the tap psi? Given psi dot max and alpha. So I give you a hint. Actually, the condition that separates the two case is that you need to find that tap psi such that you accelerate until you reach the maximum velocity, and then you need to immediately decelerate. So the area under these red lines is the delta psi that need to separate these two conditions. So you just need to find the area under these red lines. So you know so you have you have side of mass that you know, and you know that motion is acceleration motion. So you can write down the side of equal to now just want you to write down the condition that upside equal to something that already know. Okay. So I mean, the value of that upside that's separate between the case trapezoidal and the case of triangle. Okay. So it means you find the case that you have acceleration motion from here to reach psi equal to psi maximum here. Yeah, so so actually just disappear. And you know that the high is this. Using that. Yeah, you know the high of the this, and you know the slope of this line. Okay. Find the area under the triangle, right? So you already know the height of the triangle, right? And you know the slope. The slope is alpha. The slope is alpha. Or actually, because this is time, right? Because this is time, you need to know information of time. So you need to write down the acceleration equation. Acceleration equation. Psi dot equal to alpha times t, right? That while but t here actually t from the t minus ts. Don't forget. Or well, you choose tau. Yeah, you choose tau as time as well instead of this. So you can just say alpha times tau. And then when velocity reaches the maximum, what is tau? Okay. When psi dot reach psi dot max, you can find tau peak. Yeah, tau peak with tau here equal to psi dot max over alpha. So this time, this and this height, this width and height. So the area of this triangle can be found. You calculate the area. Now you already know the width of the half triangle. The width of the half triangle here. Or well, you want to find all of these, all the area under these red lines. So actually, yeah, you can find this one first, and then multiply by 2, you also get this one. Now I already gave you this for this part here. So this length here is TE minus T to the distance T minus. Yeah, TE, we know we don't know TE. How do we know? The information that we have now is that you know the slope of this, you know the slope, and you know the maximum velocity. And the start, TS? Yeah, the start, yes. This fine. And you just say, okay, so the equation for this line is this. T can run, right? And Ts, what we know. And then you can just use power is fine. Yeah.
Is the alpha constant? The
Alpha constant, yeah. Normal. Just separate this condition first. Oh, wait, well, yeah. This one is low. This one is low. Right? And now this top is this side. And you also know this side.
No, two is that. Okay, so okay, two.
Top is here.
So it's just two times. Okay, we
Yeah, so just one half this side and this. But now we have two already and then the rest.
So just two two by five, five, five max.
Yeah, so actually, let's call that upside, uh, what can I call it? Full plate condition, I say. Okay, that upside condition equal to two times go to real and one half of this uh, tau p times phi dot max.
So it's phi dot max squared over.
Yeah, phi dot max square over alpha. See, this is what we know. This is what we know. So we just first square this one divided by this. We have the left outside condition to separate. It means if what you want is that the left outside is bigger than this, then you need to generate trajectory using this curve. If okay, so if actual left outside greater than the upside C, then you need to generate trajectory using this curve. Okay, that's it. Else, you use this. Yeah, now we all know the condition to separate these two cases. Then next step is to, well, you need to find the time from here to here, from here to here. Let's call it from here to here. Let's call a tau p. Okay, and then you need to find the time from here to here. That's called tau constant. Constant, and then yeah, let's call, well, how to call it easy, acceleration. Let's call tau during acceleration, and then here uh, tau that start deceleration from here to here. Yeah, from here to here is tau, or tau tau from A to D. Okay, then here it's just call it TD. The time that start deceleration. Yeah, just call it this way. Okay, so here just call it TA. The T is absolute, tau is reactive. Okay. Yeah, here T S. Here T A. So from t, take from 0 to t peak here. From sorry, from tau s. Okay. Then psi dot equal to alpha times t minus ts. Okay. And let's call this tau. Then when psi dot reach psi dot max equal to alpha times tau, let's call it tau p. Okay, and tau p equal to 5 dot max over alpha. Then we have eta psi c equal to psi dot max square over alpha. So two cases. If delta psi c greater than, also delta psi, actual delta psi greater than delta psi c, then we have this case. Ts t t acceleration at the end of acceleration, t at the start of deceleration, and tn. Then in this case, uh, you still, okay, you still know that this area plus this area, well, this area plus this area, okay, the red one is delta psi c, right? These two area. So this area must be delta psi minus delta psi c, right? And well, so ta minus ts equal to what? Ta minus ts of course equal to psi dot max over alpha. This tau, right? Just let this, just call it tau a. How about td minus ta? Td minus ta, velocity is constant here, and the angle is delta psi minus delta psi c. So it means delta psi minus delta psi c over uh, psi dot max, right? And this one just call it tau from end of acceleration to the start of deceleration. Okay, so from here you can generate trajectory from here to here. I mean, you write the equation for velocity and then find acceleration later. Is that okay? Okay, so when you start, first start from t from here to here. Okay, so first t take from ts to ta. The equation for velocity would be phi dot equal to alpha t minus ts. Okay, and then ta, t take from ta to td. Psi dot equal to psi dot max. Okay, simple. And then td, from td to tn, phi equal to hmm? Minus alpha t dot t minus td plus, right, and then should be equal here, equal here, equal here, and then te less than or equal to t equal to 0. Any question about the other case? The other case much easier than this, right? Um, two cases, and so case one is here, and then case two delta psi less than delta psi c. So so here is t start, t at the peak, and tn. Uh, so what you have is okay, tp. You have So P actually 5. Oh, wait. So you already know the area. The area itself is delta psi, right? Delta psi. So if you know the area, you need to find TP. Okay. Um, okay. TE minus TS, which is the psi, equal to the area divided by 2 times the area, right? 2 times the area divided by the height, right? And then Tp minus T start, which is only a half of this. Like this. So it just delta psi over psi dot max. So you can find Tp. Okay. Yeah. Before actually I did not tell you how to find Ta, Td, Te exactly, but actually you can find from here, right? Okay. And so here you just have two cases. First, Ts less than T and then less than or equal to Tp. You have equation wait, phi dot equal to alpha T minus Ts like this, right? Oh, yeah. And then Tp less than T and less than or equal to Te, psi dot equal to minus alpha T minus Tp and plus what? What is the maximum velocity here? Hmm? Maximum velocity here, alpha time, alpha time, Tp minus Ts, yeah. Um, can we cancel each other? No, cancel Tp plus, oh, 2 times, oh no. Okay, so that's okay. And then Te less than or equal to T can have phi dot 0. So we can generate velocity. How about acceleration? How about acceleration? Yeah, actually you can write here acceleration. If you look at here, acceleration, it's just alpha, right? And acceleration here is just 0. And acceleration here is just minus alpha, and acceleration here is just 0. And for this case, acceleration here is just alpha, acceleration here is just dou alpha, and acceleration here just 0. Okay, then I explain the idea to generate trajectory, the same trajectory here, but for portion x and y. So now we have a vector, but not a scalar like this. So what can we do? Okay, we want to generate from this point to another point here, and what you have is maximum velocity along this trajectory, and also acceleration. Okay, you need to find two separated cases as well, because the motion from here to here for the translation, first you accelerate and then it reach maximum velocity and hold it, and then it decelerate to arrive the point. So you can make analogy from phi dot max to b velocity max, okay, and from alpha to, let's call acceleration a, and from that top side to be what, to be the distance between hy here, hy at the start and h and y at the end, right? Distance of hy at the start and at the end. Just call this, make analogy like this. And what else that you need to know? um, what else that you need to know? When you need to generate velocity, you need direction, right? Oh well, even for this case, how do you define the direction? Because it seems that we only use the positive side. For example, the rotation on this direction is positive. What if the top side is negative? Okay, so you have negative time or something inside here. So be careful. Huh? Be careful. We did not discuss about this. Actually, um, in some case, that upside can be negative, right? In some case, so we only discuss about positive to find the time okay, the time at some instant. Then very so be careful when the upside is negative. The velocity that we generate must be negative. Actually, here should be negative, right? So at the end of the generation, you should have this one equal to find this one time sine of delta psi. Okay, because if delta psi is negative, all velocity that we have generated must reverse the sign. Yeah. So what I'm writing here is suitable for numerical simulation, but it's not really. Maybe it does not make sense, right? If I write like this, okay? Careful. This is just for simulation. Yeah, I might say, uh, well, this should be always positive. I can write like this, or maybe I can put absolute like this. Okay. I can put absolute term here, in here, and here. Okay, in here, that's fine. And then I have this. Yeah, this is more mathematical term. Need to use absolute. But what about this case? Sorry, this one should be same. Absolute, 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 and then phi dot here equal to absolute phi dot times sine of delta psi. Yeah, like this. Be careful. So this one should be absolute. Okay. Uh, okay. So for this one, we deal with the velocity along the direction. But then when we want to generate the velocity component for h and y, okay, I make this analogy to have a scalar value. Okay, so this is scalar, this one also scalar, this one also scalar. Then follow the same process here, follow the same process. But finally, when you want to generate component, um, I mean velocity that has x component and y component like this. Okay, so follow the same process. You can generate, okay, let's say v can generate v of t, right? And then, but v here is scalar, and then we want to get the velocity in specific direction. Okay, so in this direction, that means um, you have that this v of t and times the unit vector in here, unit vector, and this unit vector is actually the vector h minus h start, okay, he minus h start, and here y e minus y start. This is vector, and you divide it by the distance, start and end, divided by the distance, then you get this unit vector. Okay. Right, is there any question? You think you can make a simulation by yourself after you see this process of algorithm? Yeah, this method is the simplest one, but it has a drawback. What is the drawback? Yeah, I explain the drawback a little bit so that you can catch your interest to pursue further sophisticated algorithm. The drawback is that if I want robot to move from here to here and then from here to here and then from here to there, if I use the algorithm from point to point like before, I must have the robot to stop here first before it start to here, right? So accelerate and then hold the velocity and then decelerate to zero velocity first, and then accelerate again, hold velocity, decelerate. Yeah. I cannot have continuous velocity around here, right? This is the drawback. So it is not optimal. It's not optimal. But it's a way to warm up that, well, trajectory generation can be done this way, can be done this way, and so for the case that if you only have one starting point and at the starting point, then this is fine. Okay, so we can stop now and see you next week.